have seen the expression for the force of attraction or repulsion between 2 point charges. The expression happens to be force is equal to 1 upon 4 pi epsilon naught q1 q2 upon r square. We are writing it down in the scalar notation, not in the vectorial form. Now, we would like to understand and analyze what happens if there is a medium in between the two charges. So let us say this is the charge q1 and this is the charge q2, and instead of these two charges being placed in air as they usually are, this is the expression for air or vacuum, these two charges are placed in a medium. Okay, so let us say this is the medium in which these two charges are placed. Now let us try to find out what is the expression for the force. Empirically, it is found out that the force actually decreases. Okay, so force pertaining to this particular medium is going to be written as follows: F is equal to 1 upon epsilon subscript m times 1 upon 4 pi epsilon naught q1 q2 upon r square, r being the distance between the two charges. So what do we find? Force in the medium, okay, is given as force in air or vacuum. For practical purposes, we are treating air or vacuum as the same, upon epsilon medium. Okay, so this is what we see over here. All right, if we were to write this force in more of the standard format, then we have to write 1 upon 4 pi epsilon q1 q2 upon r square. By comparing these equations, we can clearly see that epsilon naught times epsilon m gives us the value of epsilon. So I'll write that observation over here. Epsilon naught times epsilon medium is equal to epsilon. So let us now label and name the terms. This we know is permittivity of free space, so we don't need to label it again. Epsilon naught is the permittivity of free space. This epsilon m is called as the relative permittivity. Relative permittivity. And this epsilon is called as the permittivity of the medium. All right, sometimes, and confusing as it might be, but epsilon is also represented by the letter k. It is unfortunate that the number of physical quantities are much more than the number of English and Greek Latin symbols. So sometimes epsilon is, rather epsilon m, this quantity is sometimes represented by k, also called as the dielectric constant of the medium. Note that this k is completely different from this k. 1 upon 4 pi epsilon naught was also earlier represented as k. This is the unfortunate situation wherein we have got a limitation on the number of Latin and Greek symbols, but the number of physical quantities are more, and that is how it is. That is how it has turned out to be in the physics literature. So the relative permittivity is sometimes represented by k, and k is called as the dielectric constant of the medium. So using this value of k, what do we have? We have that the force in a medium can be the force in air or vacuum divided by K, K being the dielectric constant of that particular medium. So K is called as the dielectric constant, which is actually the exact same as epsilon subscript m, which is the relative permittivity of the medium. So just noting this, K is equal to epsilon m, which is the relative permittivity of the medium, which happens to be epsilon, the permittivity of the medium, divided by epsilon naught, the permittivity of air or vacuum. All right. So here we can see that K clearly, K is dimensionless. Okay, this is one thing that we can note about K. If the medium is a conducting medium, then in that case the value of K is infinity for a conductor. And that is also the reason why electrostatic lines cannot be present inside the conductor. Electrostatic lines cannot be present inside the conductor. Higher the value of K, less is the number of electrostatic lines that pass through a conductor. When K becomes infinity for the conductor, electrostatic lines become 0, and higher the value of K, lesser is the number of electrostatic lines that pass through that particular medium. Another important thing to be noted is that the value of K, the value of K is equal to 1 for air or vacuum. For air or vacuum, the value of K is 1, and the force between any two charges is going to have the maximum magnitude in air or vacuum. In all other substances, the magnitude of the force between two charges is going to be lesser than what it can be in air or vacuum.